In this video, we will be looking at compound angle formulas and how to use them to help you find exact values of trig expressions. So here we have all 6 of our compound angle formulas for sine, cos, and tan, when you're adding angles, when you're subtracting angles. And these formulas can be used forwards and backwards to help you find exact values. And before we get into that, we're just going to practice expressing each angle as a compound angle using angles from the special triangles. So I have some versions here that are in degrees. So in terms of our special triangles in degrees, we have the 30, 60, 45. We can use those angles in various quadrants. We can use 0, 90, 180, 270, 360, and any combination to try to get these degrees. So for 75 degrees plus 30 degrees is what pops into my mind. Next we have 105. When I look at 105, I'm thinking of 60 and 45. Next we have negative 15. You have different options here, but I'm going to write 30 degrees minus 45 degrees. You could also do 45 degrees minus 60 degrees. Next, we'll do the same thing, but in radians. So I have pi over 12. Now, if you look at pi over 12 and you can't think of the radian measure special angles to come up with this fraction, because that would require common denominators and all of that, you can always take your angle in radians and turn it into degrees. So pi over 12 times 180 over pi, and that's 15 degrees. And now I'm thinking, how do I get 15 degrees? 45 minus 30. Let me put those into my radian measures. So pi over 4 minus pi over 6. So that's an option. Next, 5 pi over 6. Maybe this one you can see right away because it looks like we're taking pi and just subtracting pi over 6 from it. Because pi is 6 pi over 6, and if we subtract pi over 6, we get that 5 pi over 6. You can also think of it as 150 degrees, and 150 degrees is 180 subtract 30, which is exactly what pi minus pi over 6 is. Next, we have 5 pi over 12. If I were to convert this into degrees by multiplying by 180 over pi, I would get 75. And 75 degrees is 45 plus 30. So here's 45, and here's 30. Now that we have that, let's try to use these compound angle formulas to find some exact values. So for our first 2 examples, I already have our angle written as a sum or difference of angles. So determine the exact value of cos of pi over 3 plus pi over 4. Well, pi over 3 is acting like A, it's the sum, and then pi over 4 is acting like B. So now we have to look at our cos compound angle formula, and the cos compound angle formula is cos A cos B minus sine A sine B. So now let's put our appropriate angles in. Cos pi over 3 times cos pi over 4 minus sine pi over 3 and sine pi over 4. And of course, we need to know our special triangles in order to evaluate each of these ratios and then simplify the expression. So I'll draw my isosceles special triangle, and I'll draw the special triangle that was an equilateral and it got cut in half. And now we're ready. Cos pi over 3, looking at my special triangle, adjacent over hypotenuse from pi over 3 is 1/2. Cos pi over 4, looking at the isosceles triangle, adjacent over hypotenuse is 1/√2. Now, if you would like to clean up 1/√2 to √2/2 right away, that would be great. If not, we'll do it in 2 steps. Next, I will do the same angles, but for sine, so I'm going to do opposite over hypotenuse. From pi over 3, that's going to be √3/2. And from pi over 4, that is 1/√2. I'm going to rationalize my denominators for whatever fractions have radicals in the denominator first. And then I will multiply the pair of fractions. So remember, numerator with numerator, denominator with denominator. So 1 times √2 is √2, 2 times 2 is 4. Subtract, √3 times √2 is √6, 2 times 2 is 4. Luckily, we have a common denominator right away, so we can just unite our 2 fractions, and there is nothing to collect because these are not like radicals. So that is our final exact value. Let's try another one, this time for sine. Sine of 2 pi over 3 minus pi over 2. Now, our sine compound angle formula for subtraction is sine A cos B minus cos A sine B. And our A is 2 pi over 3 and our B is pi over 2. So sine of 2 pi over 3 cos of pi over 2 minus cos of the first angle and sine of the second. I already have my special triangle for pi over 3, so that's great. For pi over 2, I will think of the base function. Now, the fact that our angle that's given is 2 pi over 3, well, 2 pi over 3 is in quadrant 2, which means sine is going to have a positive ratio, but cos will have a negative. And of course, the alpha that we would be using is pi over 3. So for my sine ratio, from pi over 3, opposite is √3, hypotenuse is 2, quadrant 2, it's a positive ratio, so we're good. For cos pi over 2, I like to use my base function. Here's the cos function, and this is 0 to start, pi over 2, pi, 3 pi over 2, and 2 pi. At pi over 2, cos is 0. That's going to make our life easier. Minus cos of 2 pi over 3. From pi over 3, adjacent over hypotenuse is 1/2, but in quadrant 2, cos is negative. And then for sine of pi over 2, again, I'm going to draw the base function. And at pi over 2, sine is at its maximum value of 1. And now this is great because √3/2 times 0 is 0, so don't have to worry about that. All I have to worry about is 2 negatives make a positive, and 1/2 times 1 is 1/2. And there is my exact value. All right, let's go to our next one where we have to work for that compound angle. We need to find the exact value of cos 13 pi over 12. Pi over 12 as an alpha is not a special angle in a special triangle, so using that by itself, we would not be able to find an exact value. So let's find a compound angle that uses special triangles. Now, 13 pi over 12, if you want, you can turn it into degrees. So if I multiply by 180 over pi, I get 195 degrees, if that's an easier way to approach this. And remember, you don't just have to use quadrant 1 angles, so like 30, 45, 60, and 90. Trying to get a combination of that you won't get 195. So sometimes you have to go in different quadrants. So when I see 195, I think of 135 degrees plus 60. 135 is just in quadrant 2, where alpha is 45 degrees. So it is going to give us an exact ratio. Now, what are these in terms of radians? Well, 135 is 3 pi over 4 in quadrant 2. And then 60 we know is pi over 3. So there's our combination if we want to turn things from radians to degrees and then back into radians. Okay. So now we are trying to find cos of 3 pi over 4 plus pi over 3. So we have cos A, cos B. Minus sine A, sine B. And now again, we're using our special triangles. So for 3 pi over 4, alpha is pi over 4, so it's the isosceles triangle, and we are in quadrant 2, which means cos will be negative, and adjacent over hypotenuse for the isosceles triangle is 1 over root 2. For cos pi over 3, we're using the equilateral triangle. Adjacent over hypotenuse is 1/2. Now we go to sine of 3 pi over 4. That's quadrant 2 where sine is positive. And we're using that isosceles special triangle again to get 1 over root 2 for opposite over hypotenuse. And for pi over 3, opposite is root 3, hypotenuse is 2. And now it's just a cleanup game. First, I will rationalize my denominators. And now negative root 2 times 1 and 2 times 2, root 2 times 3 and 2 times 2. We have a common denominator, so we can unite our fractions. So there we go. That's our exact value. Let's go in the opposite direction. What if we're given an expanded trigonometric function and we want to simplify it for ourselves? So when I look at this, sine pi cos pi over 4 minus cos pi sine pi over 4, I know that this is the sine compound angle formula for two angles being subtracted. I know it's sine because sine and cos are alternating, unlike for cos where it's all cos first, then all sine at the end. Now, in this specific example, I could evaluate this as is. I should know what sine pi is and cos pi over 4, sine pi over 4. But we could also use our compound angle formula backwards to simplify this and evaluate just a single trig ratio instead of 4 of them. So I will turn this long expression into sine pi minus pi over 4. And if I get myself a common denominator and clean this up, it will be sine of 3 pi over 4. Well, here we're in quadrant 2. Here sine is positive. We know our alpha is pi over 4, so we can draw our isosceles triangle quickly if we need to. And opposite over hypotenuse is 1 over root 2, which is root 2 over 2. We would have gotten that if we used the long expression as well. It just would have taken a little longer. Final example. Given sine x equals 4 over 5 and cos y equals negative 5 over 13, where x and y lie in the interval pi over 2 comma pi, so that means we're in quadrant 2, find the value of cos x minus y. Now, something I want to add here, find the exact value of cos x minus y, which means I can't just take a sine inverse, figure out what angle X is, take a cos-inverse, figure out what angle Y is, and then punch things into my calculator. I want an exact value, and my end goal is cos X minus Y, which means I need to know what cos X and cos Y is equal to, and I need to know what sine X and sine Y is equal to. Now, based on what was given to us, we know sine X and we know cos Y. We don't know cos X and sine Y though. However, when we are given a trig ratio, we can always draw a diagram and figure out the missing side of the triangle, whether it's opposite, adjacent, or hypotenuse. So I'm going to start with sine X equals 4 over 5. We are told that we are in quadrant 2 from the restriction. So I'm going to draw my triangle. This here is angle X. And sine is opposite over hypotenuse, which means the opposite side is 4, opposite to this angle here. The hypotenuse is 5, and we need to find the adjacent side. Because if we find the adjacent side, then we'll be able to figure out what cos X is equal to. So I'm just going to do a little Pythagorean theorem. So I'm going to write 4 squared plus x squared equals 5 squared. I chose x because I'm looking for a length on the x-axis, but you could have used any letter. So x squared equals 25, subtract 16 when that 4 squared moves over. That's 9. And when we square root both sides, x can equal positive or negative 3. Because we're on the negative x-axis, I'm going to label negative 3 as my adjacent. So now I know that cos x is equal to negative 3 over 5. So now I have this information. Now let's repeat the process for cos y equals 5 over 13. So we know for cos, it is adjacent over hypotenuse. The adjacent side is negative 5. The hypotenuse is positive 13. Remember, the hypotenuse will never be negative because it would represent the radius of the circle created by that terminal arm swinging around. So again, another quick Pythagorean theorem. Negative 5 squared plus, I'm going to use y squared this time because I'm looking for the vertical, equals 13 squared. 13 squared is 169. Negative 5 squared is 25. When it moves over, it becomes negative. And I get 144 for y squared. When we square root, it's positive or negative 12. Looking at our diagram, we're above the x-axis, so this is going to be positive 12, which means sine y, opposite over hypotenuse, is 12 over 13. And now I have the last ratio I needed. And now we can put it all together. Cos x is negative 3 over 5. Cos y was given to us, negative 5 over 13, plus sine x was given, 4 over 5, and sine y we just found, 12 over 13. And now just multiply your fractions and add them up. So we will have 15 over 65 plus 48 over 65. We already have a common denominator here, so we just have to add our numerators. And we get 63 over 65. So we have seen a variety of questions using the compound angle formulas. Ones where you're given the compound angle and you just have to set up the formula, do your ratios. Some where you have to find your compound angles and then use the formula. Others where we're given a long expression and we want to simplify it using our compound angle formulas. And finally, a little visual scenario where we need to use some Pythagorean theorem to help us use the compound angle formula to find an exact value.